All right, topic 8.1, do now. So I'm honestly just gonna skip the do now. All right, so yeah, this unit is about waves. We have really just two more units left. Well, including this one, so just one more unit. But we're essentially going to be talking about waves, right? So waves are repeating propagations disturbances, usually are repeating patterns. As you can see in this GIF right here, the top GIF, right? So you see a spring and a mass, and it's going down and up and down and up. Right, this is a repeating pattern, and we can graph that pattern by drawing it as a wave, right? As you can see, the corresponding yellow dot corresponds when the mass goes up, then goes down, then goes back up, and then goes back down. Right? And so there's an equilibrium position at the middle of the line. And that's where it would be, well, if it wasn't doing anything. But right now there is a repeating pattern. And there's a vocabulary word here, right? To propagate. To propagate is to be transmitted in a certain direction or through a medium. Right, so essentially, this wave is moving in a certain direction. It's propagating in a certain direction. And a medium means just any object a wave travels through, wherever object the disturbances go propagating through. Okay. And I could show you this in real life, right? So we're going to learn about two different types of wave, or rather two different waves, two different ways waves actually propagate. And the first type of wave is called longitudinal. Now, if you were in class, I could show you this, right? I showed you how waves actually propagate as they move to the right. So longitudinal waves vibrate parallel to the direction of propagation. This is very important uh, because we can't just say left to right as what's happening here. And so let me just demonstrate it by taking a snapshot, right? So we have this. So you have a wave here, right? So let's use red. So you have a wave, you have a longitudinal wave going this way. And well, if your longitudinal wave is propagating to the right, well, your waves are going to vibrate parallel. So it's going to start vibrating left to right, left to right. Now, on the other hand, well, if my wave was moving up, right? If my wave was moving upward, well, then my waves are going to start vibrating parallel. So it's going to vibrate up and down, right? It's parallel to the direction. On the other hand, transverse waves, they vibrate perpendicular, right? So what that means is, well, as the wave is moving to the right, right? So the wave is going to vibrate perpendicular, so the wave is going to vibrate up and down here as your wave is moving to the right, as it's propagating to the right. And it's even further important that we just clarify the distinction here between perpendicular and parallel because, well, again, if the wave is moving down, I mean, rather up, well, then your waves are gonna vibrate uh, left and right because again, it's perpendicular to the direction, and it's something really important, right? So let's move on. And as you can see, right, as you can see here, it's your transverse wave on the bottom is vibrating up and down as your wave moves to the right. So characteristics. So what I'm showing you right now is a sound wave, right? And sound waves are longitudinal waves, which means they vibrate parallel to the direction of motion. And so they're propagating through air molecules, and so your air molecules are going to be your medium. And this is one really important question, right? So in a sound wave, do the particles themselves travel outward or do they just vibrate back and forth? And how can you tell? I want you guys to look at the particles themselves. They look very closely. Do they actually go away? Do they go outward and we forever lose those particles? And as you can see, right, as you can focus in and as the bottom right GIF shows you, that particles don't really move from the general location. They vibrate back and forth, sure, but they don't really go anywhere. They're not being transferred anywhere. Waves don't transfer matter. Waves don't carry a particle to another place. Rather, waves only transfer energy. And something written here at the end of this paragraph. Waves only transfer energy, not matter. And it's something extremely important. Well, but what actually does go, what a wave does transfer is energy. As you can see, the wave propagates outward. All right. So let's do a practice question, right? So an earthquake is traveling from west to east through a rock. So you have an earthquake here. The earthquake is going west to east. And the particles are vibrating in a north-south direction, so up and down. So north-south, the wave must be what type of wave? Well, instantly you should know that transverse waves vibrate perpendicular and longitudinal waves vibrate parallel. So, your waves right here, your particles are vibrating north to south and it's perpendicular. So the answer here is A, transverse. The reason why is because your particles are vibrating perpendicular to the direction of motion. And so here, the parts of a wave, the top of a wave is called a crest. Right, so the top of a wave is called a crest. The bottom of a wave is called a trough. Right here, trough. The max height a wave reaches from equilibrium. Where is my tablet marker? Okay. The max height a wave reaches from equilibrium is called the amplitude. So right here, right? So your amplitude right there. And a complete wave cycle, one up, one down, right, is called your wave length. Right, which is kind of represented by this word over here, right? This wavelength lambda. All right. Good. Now again, your equilibrium point is really this middle line right here. It's a state where pretty much where it normally the object normally is, or where everything would be if there was no wave, where there was no disturbance. Okay, and that's your equilibrium. All right, so let's move on to part 2. So again, the larger the amplitude, the more energy you will have. That's really the relationship that you should understand, is that, well, the more, again, more amplitude, higher amplitude, larger amplitude, more energy. Lower amplitude, less energy. Wavelength. And so essentially, wavelength is just the length of a wave cycle. Right, the length of a wave cycle. So as the wave is moving, right? So you can either classify it as either one up, right? So one up, one down, and so actually it'd be better if I use a different color, right? So one up, let's use this. So over here, that's one up, right? So this is one up, one down, and then here, and so this would be one wave cycle. And so this would be the wavelength of the wave, and we call this symbol lambda. Now, alternatively, you can think of it this way, right? So a wave can also not only be a one up, one down. It can also be classified as trough, or rather crest, the highest point of wave, to the next crest. And so this would be classified as was a wavelength either. This would be one wave cycle, and you can take the length of this wave cycle as its wavelength. Alternatively, it's also either a trough to trough, right? And so that could also be, you could also get the wave cycle that way, and you could calculate the length of that wave cycle by doing trough to trough. So any one of these three possibilities, any one of these three methods, you could use to calculate the wavelength. Frequency is really how many wave cycles that occur per second, right? So if you have a high frequency, you have more wave cycles that occur. If you have a low frequency, well, you have less wave cycles that occur, right? And so it's measured in hertz. So parts of a wave, let's do this practice. Is wavelength of the waves equal to the distance between which 2 points? Now let's think about it, right? And it's rather simple once you kind of take a look at it. So, and I gave you the GIF as a way to kind of visualize what this diagram is saying. And we're going to focus on this diagram up here. Now, it might be difficult to figure out, well, what does this diagram mean? And this diagram is showing you a longitudinal wave. I'm letting you guys look at the GIF a little bit longer. Right, so as this wave is moving right, the longitudinal wave is propagating to the right. Right, and you can kind of see what that looks like. And the diagram, the purpose of this diagram right here is to kind of show you that on 2D. Obviously, you can't have a GIF on a test. So these lines right here, right, these compressed lines, these lines where they kind of look, they're really close together, they correspond to these parts over here, right? So you see these compressed particles, and that's where they correspond to. All right. And so on a wave, if we were to draw it in like a transverse wave, well these lines right here, these compressed lines, they would correspond to the crest of your wave and the crest of your wave and the less compressed parts. I'm sorry, I'm gonna mute my mic for a second. So the less compressed parts would correspond to your troughs, right there. And the question is asked you, well, which 2 points would represent the wavelength of your wave? Well, we know that the wavelength of a wave can either be one up, one down, or crest to crest, or trough to trough. So we want here, I think it's easier to kind of look at crest to crest, right? So we want crest to crest. So this kind of makes it easier for us because, well, we want this location and we want this location, we want this, and it turns out, well, C and A are kind of equally distanced from each other near the compressed parts of our wave. And well, the answer is A and C, right? A and B really isn't a wave cycle, right? Because B is kind of somewhere over here, and that's not really. These 2 points are not really wave cycles. B and C also not it, right? And B and E, well, that's more than one wave cycle, right? Because E would be over here on the right hand side, so this would be E, and this would be B, and that's definitely more than one wave cycle. So the answer here is B. The energy of this wave is related to its what? As we previously learned in one of the previous slides, amplitude is your energy. The amplitude of the wave is equal to the energy of the wave. All right. So which diagram best represents the motion of the particle at position C? Again, this is a longitudinal wave. right? And longitudinal waves vibrate parallel to the direction of motion. If your wave is moving to the right, well, as indicated over here, wave movement, well then your particles are gonna vibrate parallel to the direction of motion. So the answer here is D. Now this is a hard question. This is something students kind of need to visualize for themselves. There's no amount of explaining that I can do that can help you visualize it other than just really just looking at the GIFs, looking at the image. So let's take a look at one of these red dots. And we'll have you guys look at the red dot, the third red dot. So I'm gonna show you guys what I mean. So let's focus on this red dot right here on the image, okay? So I know the slide says first color particle, that's fine. We're gonna do the third color. So as this wave is propagating to the right, in which direction would the third color particle go? Now most students are gonna say it's gonna go up. Right? Most students are gonna say it's gonna go up because they think, well, the wave is moving, and then which means the particle is moving. But in a previous slide, we also said that, well, particles, they don't actually move with the wave. They're not getting transferred. This particle right here follows the line of the wave. And so let's actually play this GIF, rather this video. I want you to focus on the third red dot and focus on at the same position where it is right now. Right? So at the same position, well, as the wave is moving to the right, you'll see that the red dot, the third red dot, is going downwards at the same position in the image above. It's going downward. So let's kind of explain it a bit, right? Explain what's happening. And this is something rather difficult for students to kind of visualize. It really just takes experience. So as your wave is moving to right, you can see that I essentially move this image of my wave a little bit to the right each time. So this is really the first image and the second image, right, and the third and the fourth, and then so this is as time goes on. Time goes on. And in each image, you'll see that the wave moves to the right. Right, the wave is moving to the right, but the particle itself is staying on a line. Right? The particle can only move either up or down. That's essentially what's happening here. Right, as the wave moves to the right, well, because it's the transverse wave, this particle can only move up or down. So it's going to either stay on this line over here. Well, as your wave is moving to the right, well, the dot has only one place to go. It's going to follow, it's going to go on the line of the wave. So as the wave moves to the right, you'll see that the particle goes downward and follows the path along that wave, right? And so then as the wave continues moving forward or moving to the right, well, the dot, the particle will follow the path on that wave, will continue to follow the path, right? Because the wave is moved to the right now. And so on and so forth. And so the particle will continue following the path. Right? So the particle will continue following the path there as the wave moves to the right. I honestly suggesting that there's no really other way of me explaining this. You just have to visualize this for yourself. Look at the video. Look at the loop video. Try to figure out where will this particle go as the wave is moving to the right. Now here's an easy way to think about it. If your wave propagates to the right, well then your particle will be on the position to its left. Right, and so what that means, actually, I should probably change this. Let's actually say your particle propagates to the right, then your particle will follow the line of the wave to the left. Your particle will follow the line of the wave to the right. All right, okay. So that's really just two ways to remember it, right? So if your wave propagates to the right, then particle will follow the line of the wave to the left, and your wave propagates to the left, then your particle will follow the line of the wave to the right. So those are two general rules, and we're gonna go back to them because just you'll understand what I mean when I say that in just a bit. So let's say this has this practice problem, right? The diagram below shows a transverse wave moving toward the right along a rope. And then at the instant shown, point P on the rope is moving towards what? Alright, so now this wave is moving to the right. This is a transverse wave, so there are only two ways you can vibrate. You're gonna either move up or down, so it's answer choice C and D are automatically incorrect. So again, if the wave is moving to the right, you want to look at its position to the left. Look at the wave to the left, and then the particle will be along that line, along that wave in the future. So it's going to go up. I'm going to show you what that looks like, right? So let's say this wave moves. This wave moves to the right. Right, this particle can only move up or down. So now the particle is going to be over here, which is essentially above the equilibrium line, right? So I'm gonna draw our equilibrium line right here, and you can see, well, the particle was originally over here, right? So the particle was originally over here on this wave. Well, now as the wave moves to the right, the particle follows the line of the wave, and now the particle is moving up because now the particle's new position is over here as time goes on. Right? Again, the wave is moving, and the particle really only follows the path of the wave. Rather, it goes along the line of the wave. The next practice question. So now you have a wave propagating to the left. And again, it's a transverse wave, which means it can only either go up or down. So it's neither choice C nor D. So as this wave is moving to the left, right, we want to look at the line to its right, and so what we say, well, it's going to follow this line down here, and it's going to go down, then up, then down. Right, so again, if you don't believe me, well, let's just think about it, right? Let's say this entire line moved. Actually, draw my equilibrium line there to help myself. Right, so as this wave, right, so it only moves up or down. So now its new position is over there. Guess what? Guess what? Well, it moved down, right? It followed the path of this line. So it moved, its new position is now over here if the wave goes to the left, all right? And so as time goes on, well, it's going to go down, then up, and then down. And so its answer choice is B. All right.